Okay, good evening all, and welcome to the problem solving course on coordination chemistry, which is taken by Professor Debasis Ray from IIT Kharagpur, and I am Satyaprakash Yadav, a PMRF scholar from August 2020 batch to present, and I am working under supervision of Professor Satish Patil from SSU Department, Indian Institute of Science, Bangalore, India. So about the course, it is a 12-week course. In week one, basically we have discussed about what is the coordination complex and their introduction and definition, and we have went to the classification of ligand, basically classification ligand of 1, 2, 3 types. And in week two, we have discussed in detail about the nomenclature of the coordination complexes and solve the problem based on that. In week three, we have discussed the different coordination number starting from 3 to 12 and their stereochemistry, basically where we have discussed the structural isomerism. Then we have discussed the stereoisomerism. In that we have discussed the cis-trans isomerism, which is geometrical isomerism, and then we have the stereoisomerism. And yeah, week four, basically we discussed in detail the structure, symmetry, isomerism, and in that we have discussed the coordination equilibria. Basically here we find out what is the different kind of formation constant, what is the overall formation constant, and how we use in these things in the coordination complexes. And in week 5, basically we have discussed in detail the different kind of bonding in the complexes. So in week 5, we have discussed uh, valence bond theory in detail and little bit about the crystal field theory. In week 6, we have discussed in detail about the crystal field theory and what is the John Taylor effect in split crossover. In week 7, basically we are going to discuss about the optical spectra, and then we will discuss about the what is the DT transition, and the in final lecture we will discuss about the charge transfer spectra. So first I will briefly introduce what are all those things, and then I will go to the problem solving session. So first thing is that the electronic spectra of transition metal complexes. So the transition of electron from one level to another level. So one level which is lower in energy, basically it is a ground state, to another level which is higher energy level, and we basically called it as a excited state. So the transition of electron from one level which is lower in energy, or we basically called it ground state, to the higher energy level which is an excited state involve absorption of energy at a particular wavelength giving electronic spectra. Okay, so we have, like suppose we have one ground level, we have one excited So this is your ground state. This is the excited state. Now there are two types of light. This is the absorption, so which has one corresponding lambda. So we will get the absorption spectra like absorption versus lambda, and we have like a spectra like this. So this is our lambda max, where maximum absorption of light is there. So this transition generally occur by absorption in UV visible region, which is our region from like 1 into 10 to the power 5 to 10 to the power 4 centimeter inverse, which is 100 nanometer to 1000 nanometer. Okay, so and another way to say that, like more common region is 200 to 1000 nanometer. Okay, so if I see like 200 nanometer to this, we can divide like three region. So 350 to 750 to 1000 nanometer. So this 350 to 750, which is color. Above that it is no color. Below that also there is no color. Right? So one of the very important thing is that Beer-Lambert's law in the electronic spectrum. Beer-Lambert's. So I will write. So we have, suppose one light is coming. We have a monochromator, basically a prism, which will give a monochromatic light of intensity I0. We have one solution. Suppose 1 centimeter. This is the cubit. In that solution is there. After that, we are getting the intensity I. Okay. So I will just write, when a monochromatic light is passed through a solution. Okay. So the intensity is basically intensity that decrease in the intensity, which is like absorption, is directly proportional to concentration. Absorption is proportional to length. So that concentration, this is given by Beer's law, and absorption is proportional to concentrate length. This is called Lambert's Bourke law. Okay, so together we called it like Beer-Lambert's law. Okay, so what we have like, so here the intensity, the like final intensity, which is epsilon I0 e power minus epsilon Cl. So we can write it like log I0 by I is log e power epsilon Cl. So this quantity is called like absorption or optical density is epsilon Cl, because log e power. So here the important thing is that epsilon is the criteria to determine to determine the type of transition. So what is the unit of epsilon? Epsilon is A by Cl. So uh, uh, this is basically, this don't have any unit. It has C has mole per liter, and this has centimeter. So you can write liter mole inverse centimeter inverse. That is the unit of epsilon. Now from this epsilon, we can know that whether it is a DD transition, or it is a ligand transition, or it is a metal charge transfer transition. Right? So what are the different types of electronic transition in the coordination complexes or in the metal complexes. So we have first characteristics of metal. Characteristic of metal ion, which is DD transition. Second, we have characteristics of ligand, which basically we are getting from the ligand transition. Third, we have characteristics of complex. Is basically our charge transfer. Whether it will be ligand to metal or metal to ligand. There are two kinds of charge transfer. Now if I roughly draw spectra, how it looks like, it will be if I absorption versus wavelength. So suppose it is 200, 300, 400, 500, 600, 700, 800, 900, like that. So first we will having like initially we have like some sharp transition, which is your ligand transition, which will come in the region of 2 to 400, and then we have like something abroad, which is charge transfer, and finally we will have like a small and broad kind of DD transition. So we can see that epsilon is highest for ligand transition, then charge transfer, then DD transition. So we can draw what is the characteristics of the electronic transition. So next thing is characteristics of electronic spectrum. So basically the how or what are the things? First is that absorption wavelength. So which is lambda max. Second criteria, what we can see that is the bandwidth. Third criteria is the molar extension coefficient. Which is epsilon A by Cl. Right? Now we can see that each and every one. So we will write dt. We see that where the lambda max is, what is the bandwidth, and what is the epsilon max. So for DD transition, lambda max will basically rise from 10,000 to 30,000 centimeter inverse, their bandwidth will be an order of 3000 centimeter to 1000 centimeter, and their epsilon is very big, like 5 to 10 liter per mole per centimeter inverse. For ligand transition, their lambda will be 50,000 centimeter inverse, 50,000 to 10 to the power 5, 1 lakh centimeter inverse. Their bandwidth will be very small, like 100 centimeter inverse, and their epsilon will be 10 to the power 5 to 10 to the power 6 liter per mole per centimeter inverse. For charge transfer will be in between dt and ligand transition. So charge transfer will be 30,000 to 50,000 centimeter inverse. Their bandwidth will be close to 1000 centimeter inverse, and their epsilon will be 10 to the power 3 to 10 to the power 4 liter per mole per centimeter inverse. Right? So next thing is that why dt transition is broad. That is the question. So the very simple way is that, like, we will draw the so I will write here also y dt transition is broad. Okay, so suppose we have T2G orbital, we have G orbital. So this T2G orbital will be having the small level, like so what is that, like they will be having the vibrational and this is your rotational. So we are having like we are having electronic level, we are having the electronic level. In between we have the vibrational level. In between vibrational level we are having the rotational level. Right? So all three transition occur. So suppose what we are having here, one transition can go here, it can go from here to here, can go from here to here, like that. So this vibrational energy level will be 100 of dt transition. Rotational energy level will be 1 of 100 of vibrational energy. Right? So the very important reason is that in the dd transition, there are many rotational and vibrational energy level, and this existing of vibrational and rotational transition along with electronic transition is responsible for the broadband. So why DD transition is broad is basically because we have vibrational energy level between the electronic energy level, and we have rotational energy level in between the vibrational energy level. So the existing of vibrational and rotational transition along with electronic transition is the basically reason for the broadband. Second reason is that John Taylor distortion. We have already discussed previous class. So John Taylor distortion, like we have like T2G, EG, it will further split into two different kind of energy level. Now we have actually 1, 2, 3 transition. So there are 3 transition, that's why we are having. And the final third region is the spin orbit coupling, which we discuss in the next video. Spin orbit coupling. So these are the 3 regions why the spectra is broad for the DD transition. Now there is the selection. Now come to the selection rule. So what is the selection rule? Selection rule is like uh, selection rule. We'll come to the selection rule for the DD transition. DD transition. So what is that? So there are many possible transitions. Many possible transition, but all is not allowed. Not allowed. Only few are allowed. Few are allowed. Right? So there are transitions. Some are forbidden transition, optional. Okay, so it is not necessary that all theoretical transitions are absurd. Some of them are absurd, called some of them are absurd, they are called allowed transition, and some of them are not allowed, these are considered as forbidden transition. Okay, so first thing is that there are many theoretical possible transitions. It is not necessary that all transitions are absurd. Some of them are absurd, called allowed transition. Some of them are not allowed, called forbidden transition. And some of forbidden transitions are also observed due to relaxation and deviation in the selection rule. They are weak and far less intense. So I will just write those statements. So there are many theoretical possible transition. It is not necessary that all the transition are absurd. Some of them are allowed. Some of them are absurd, called allowed transition. Some of them are not absurd. They are called forbidden transition. Right? And one important thing that some of the forbidden transition also absurd. Why? Due to relaxation or deviation in the selection rule. But the important thing is that these are these are these are peak and less intense. Less intense. Okay. So how many types are selection rule is there? There are two types of selection rule. First one is the Laporte selection rule. What it said there? It says that the electronic transition between set of same orbital is sorry orbital is not allowed. It is allowed when there is change in subsidiary quantum number. Subsidiary quantum number. Okay, means if delta L is plus minus 1 allowed, delta L is 0 fault. Uh, DD transition is Laporte forbidden, but it is observed due to relaxation in selection rule. So what is happening? So in DD transition, what happens? There is a PD mixing. Because of that, delta L is not equal to 0. That is it. Second thing is that spin selection rule. What is said that electronic transition accompanied change in spin are not allowed. So delta S is 0 allowed. Delta S not equal to 0 fault. So I will just introduce one or two more slides and discuss the okay. So just see that what are the types and how we are seeing. So the orbital, we will take orbital selection rule means Laporte. We will having the spin selection rule. We will be having the types of transition, and we have the epsilon and we have the example. Stable is very important. So first thing is that suppose this orbital selection range is allowed, spin is also allowed. The types of transition is called charge transfer. where epsilon is 10,000. Example are TiCl6 2 minus. So partially allowed, if suppose that laporte is a partially allowed, like there is some PD mixing. PD mixing is been allowed, that is called, that is comes under the category of DD transition, and it has that epsilon close to 500. Example CO Br2 minus, Br4 2 minus. Second, suppose this is forbidden, this is allowed, this is again come in DD transition, it will be come in 8 to 10. Example is TiH2O6 3, sorry, 2O6 3 plus, vanadium H2O6. Fourth is like suppose this is partially allowed, this is forbidden, this again also come in DD transition, this is having only 4. This is the example, like suppose all the manganese complexes where DD transition is forbidden, they are always fade in color. Now suppose this is also not allowed, this is also not allowed, this again come in the DD transition, they have very small epsilon, this come under like MnH2O6 H2O6 2 plus. That point 2 is also because of the bichronic coupling. So this is the very important table. Now if I ask, we have one octahedral complex, we have one tetrahedral complex, which one will be having the higher epsilon octahedral, epsilon tetrahedral. So epsilon tetrahedral will be larger than epsilon octahedral. Why? Because this is more symmetric, less PD mixing. This is less symmetric, more PD mixing. That's why epsilon tetrahedral is greater than epsilon octahedral. Now I will not go into the detail of the term symbol, okay, but little bit I will go and just go to the charge transfer. So the term symbol, in the term symbol, what is term? Term is nothing but your bare energy level. So we have this quantum number. So n is your basically determine the size and energy. L is determined by the shape and momentum. M, what is it determining? And yes, it can be plus minus half. And J is the resulting quantum number. So the microstate, like suppose for example for P2, how many microstate are possible? System. So first of all, what is microstate? So each different arrangement of electron in a set of orbital having different energy gives the microstate. Microstate. So the what is the formula for number of microstate is? Number of microstate is basically NCR, where NCR is n factorial, R factorial, n minus R factorial. So what is n? N is the twice of the orbitals. R is the number of electrons. Number of electrons. Suppose for P2, so number of microstate will be 6CR, means 6 factorial divided by 4 factorial into 2 factorial, which is 6 into 5 divided by 2 is 15 microstate. So for D2, so D2 has twice the number of orbital, D has 5d orbital, it is 10C2. That is 10 into 9 divided by 2 means 45 microstates of gas. Okay, so this all the LS coupling and those things I will discuss during the question answer session. Now I will go to the question answer session. In a aqueous solution of plus 5 state of vanadium, vanadium metal ion will give the color A violet color, B green color, C yellow color, and D blue color. Can you write in chat box that what will be the answer for question number 1? Okay, so let me say this is in the first lecture where professor has discussed like what is the different oxidation state and their color. So if we see that vanadium 2 plus is basically violet, vanadium 3 plus is green, vanadium 5 plus is blue, 4 plus is blue, and vanadium 5 plus is yellow. Now how this color is coming? So basically professor has discussed that color wheel. So where we have like uh, whatever wavelength it will absorb, the complementary color it will give. So the if it is this is the violet, this is blue, then we have green, then we have yellow, and then we have orange, and then finally we have red. So if it is absorbing the violet, means it is absorbing in the range of 400 to 430. This will give the complementary color of yellow. That is the concept here. So why why vanadium metal is colored? Because of the electronic transition. Second thing is that like where it is absorbing and what is the color for that complex. So it is absorbing the violet region, that's why it's giving the yellow color. Second question is, through the DD transition is Laporte forbidden, is give color in solution because of. Can you write in chat box what will be the answer? I will wait for a few seconds and then. So the option is it is a high energy transition, it is a low energy transition. Spin allowed in some cases. D is the Barnum coupling. So if you are here, so I have written like why like DD transition is Laporte forbidden, but it is coming like still we are seeing the DD transition. The reason is the PD mixing. PD mixing. and that is because of the Bardronic coupling. So I have given also that example, like why the tetrahedral complexes are more intense than the octahedral complexes. The reason is very simple, because octahedral is more symmetric than the tetrahedral, like, and that's why that in octahedral there is less PD mixing, while in the tetrahedral there is more PD mixing. So that PD mixing, which is bibronic coupling, is the responsible for the giving the color in DD trans. Okay. So what is the S and L value of 15 and atom respectively? Okay. So I will wait for another few seconds and then Muhammad, can you guess what will be the answer for this question number 3? Am I audible to you? Can you write in chat box that I am audible to you? Okay, no problem. We'll go. So first thing is that here we have to discuss. So there is one term called L, which is the resulting orbital angular momentum and right quantum number. So this is the azimuthal quantum number basically. So your L is nothing but all L1 plus L2 plus L3 plus L4 dot dot dot. Right? So if L has the value 0, it is called S. It has 1, it is called P. It has 2, D, 3, F, 4, G, 5, H. Like that we have that. These are the spectroscopic terms. Are called spectroscopic term. And what is the S? Your S is basically the S1 plus S2 plus dot 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 Sn. This is called the spin quantum number. Okay, so now we will write what is the 15N. 15N is nothing but 7N15. So it has 7 electrons, so it will be 1s2, 2s2, 2p3. Now we will, because these are closed, they will not participate in that quantum number, so this is 2p3. The outer orbital I will draw the structure quantum number. So 1, 2, 3. So this is 0, this is plus 1, this is minus 1. So what is the rule says that how we will assign the electronic type. So rule says that maximize the orbital quantum number. Means electron filling start from the higher quantum number. So it has 3 electrons. So higher means first one it will go to plus 1, second it will go to the 0, 1, and third one it will go to the this one. Second is that maximize the spin momentum means Hund rule. So all will be in the, if it is in the all degenerate state, singly it will be occupied. And third will be L plus S is equal to J. L plus S is equal to J means for more than half field, and if L minus S, that is for the less than half field. But that is the different case. Here only this much is required. Now we will just write what is the L. L is plus 1 plus 0 minus 1. L is 0. What is the S? S is 1 by 2 plus 1 by 2 plus 1 by 2 is 3 by 2. So your S value is 3 by 2, L value is 0. That is the correct answer. Okay. So second thing is that light pink color of COH2O6 2 plus and deep blue color of COCl4 minus 2 are T2. What is the reason for COH2O6 2 plus is light pink color? Light pink color. While COCl4 minus 2 is deep blue color. Can you write in chat box what is the reason for this uh, uh, um, uh, what is the reason for COH262 plus is light pink color while COCl2 minus is deep blue color? Okay. Yeah, either you can just tell me what is the difference between COH262 plus and COCl2 minus. Okay, so I will just tell you. This is octahedral complex. This is tetrahedral complex, right? So this delta octahedral will be greater than delta tetrahedral. That is the first concept here. So this will absorb your COCH2H2O will absorb the blue wavelength. This is absorbing the blue wavelength. Blue wavelength absorption. And this will absorb the lower energy. This is your absorbing the red wavelength. Red wavelength. Why? Because of the uh, splitting between the d orbital, which is the your crystal field extraversion energy. Now, if it is absorbing the blue wavelength, the complementary color is the pink color. If it is absorbing the red wavelength, the complementary color is the blue. That is the second concept here. What is the third concept? First one is the light. That octahedral complex is light. Tetrahedral is complex is the deep blue color. Question is why? The answer is that PD mixing. So PD mixing will be less here and more here. Why? Because tetrahedral is the uh, centrosymmetric. Tetrahedral is the octahedral is the centrosymmetric complex where we have less number of PD mixing, and tetrahedral is the non-centrosymmetric. There we have more PD mixing. That's why epsilon tetrahedral is greater than epsilon octahedral. So this is the three concept here for the question number 4. I hope you got it. Question number 5 is the what is the term symbol for the ground state of the nitrogen atom is? 3p0, 4p5 by 2, 1p2, 4s3 by 2. Can you just write in chat box? I will just wait for 30 seconds and then I will go and explain how it's come. Okay. Okay. So let me just rule. So what is the rule? What is the rule for L, S and C? So your first rule is that maximize L. Second rule says that maximize S. Third rule says that L plus S is equal to J for more than half filled. L minus S is equal to J is less than half filled. Right? So now I will just write. So nitrogen is 7. So this is 1s2, 2s2, 2p3. That this is the responsible. So I will write. So electron filling will start from, this is plus 1, 0, minus 1. Electron filling will start from higher azimuthal quantum number. So 1 electron, second electron and third electron. By this way, we are maximizing the orbital quantum number and the spin quantum number. So L is plus 1, plus 0, minus 1. L is 0. What is S? S is 1 by 2 plus 1 by 2 plus 1 by 2. This is 3 by 2. So now we have L plus S. Now how we will write? So L is equal to 0 means spectroscopic term is S. What is 2s plus 1? 2s plus 1. So how we will write? We write like this. L 2s plus 1 J. So what is 2s plus 1? 2s plus 1 is 3 by 2 plus 2 into 2 plus 1, which is 4. So here S, then 4, N, J. J is L plus S because L is 0. So S is 3 by 2. So the electronic term symbol for the ground state of nitrogen is 4s3 by 2. I hope you got it this one. Sixth question is for the complex ion Cu NH36 plus 2, the number of possible DD transition will be. How many transition will be possible for the Cu NH36 DD transition? So this I think I will discuss detail in the next lecture. So this is D9 configuration. So we have D9 and it has term symbol 2D. So we have 2D. So here 2EG, 2T2G, like this it will happen. There is only one electronic transition. This I will discuss in detail in the next lecture once I will discuss about the orbital diagram. There I will discuss in detail what is the concepts of hole formation and electronic transition. All those things I will discuss. So I think this one will be the EG and this is 2T. The compound which shows MLCT is metal to ligand charge transfer. Option A is K2Cr2O7. Option B is NiCO4. Option C is HgO. Option D is NiH2O6 2 plus. Can you just tell me what is the answer for this question number? Just wait. So what is the criteria for MLCT? Right? So metal should be in high oxidation state. No, metal should be in low oxidation state. means it should be having the reducing character, reducing agent. In your ligand should be in the oxidizing, right? So metal should be reducing, ligand should be oxidizing. So metal ligand transition observe where metal will be in low oxidation state and ligand having low lying pi star anti-bonding orbital. So the ligand like CO, SCN, NO, these are like ligand, they have low lying anti-orbital. They form that metal to ligand charge transfer. So what happens? Metal d electron transfer from metal to ligand pi star. So this is the electronic transition happen. For ligand to charge transfer, opposite should happen. Metal should be oxidizing, ligand should be reducing. So what is happening? Like K2Cr2O7. Here chromium is in the +6 oxidation state. So metal is in high oxidation state. Ligand to metal charge transfer will happen. So here oxygen electron transfer is happening from oxygen to chromium. NiCO4 here metal to ligand charge transfer is there because nickel d electrons are transferred to pi star of CO. That is the correct answer for this. HGO is again ligand to metal charge transfer, and this is there is no ligand transfer. Here is only DD transition. Okay, I will go to the next question. The complex MnH2O6 plus 2 have very light pink color. The waste region is presence of 2T2G ground state and the complex does not have the charge transfer transition. Presence of 2T2G ground state and DD transition here are orbital forbidden but spin allowed. Presence of 6,1G ground state and DD transition here are orbital allowed but spin forbidden. Presence of 6,1G ground state and DD are both are spin forbidden. So what is the reason? So first, this is the D5. So D5, if we draw 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So this is plus 2, plus 1, 0, minus 1, minus 2. So L will be 0, S will be 5 by 2. So this is the S microstate. 2S plus 1 is 6. So this 6S 5 by 2, that is the your ground state. This s orbital will split in one. This is called uh, G-rate. So 6A1G will be the ground state. I will discuss in detail once I will discuss about the orbital. So here this is first thing is that this is the s orbital. So this is for in this both orbital and sphere orbital. That's why most of the manganese complexes are very uh, very less intense, or we can say they are very feeble in the color. Question number 9. The increasing order of the wavelength of absorption for the complex CrNH36, CrCl63, CrH2O plus 3 and CrCl3. What will be the increasing order for the complex having this? So here the thing is that we have to go to the help, take the help of spectrochemical series. That is the first thing, right, which we have to take. Now in spectrochemical series we know that X donor, then O donor, then N donor, and then C donor. Now we have first it will come COCN, then it will come NH3, then it will come water, then finally X. So CNOX means 4 will be the first, then first, then third and second. That C option is the correct. Now then, which of the following statement is not correct? Complex with strong field ligand uh, absorb high wavelength light. Color change with the strength of ligand attached. If the compound absorbs violet light, it will appear yellow. Color of complex depend on the crystal field distribution energy. I will wait for some few seconds and then I will discuss. Okay, so uh, complex with strong field ligand absorb the higher wavelength. That statement is not correct. Why? Because we have strong field ligand field means more splitting energy, means delta octahedral will be increasing. Delta octahedral will be increasing means it will absorb the lower wavelength, but it is saying the higher wavelength. This is the statement which is not correct. While color change with the strength of ligand attached, definitely, because with the change with the strength of ligand, the delta octahedral will change. That will absorb different color and complementary color will change. If the compound absorb violet, will appear yellow, because definitely it is because of the color will. If we see, we can say that if a compound is absorbing violet, it will give the yellow. What we see in the case for the vanadium 5 plus. Color of complex depend on the crystal field extravasation energy. That is again the same statement which is coming from here. Complex that absorb the shortest wavelength. I will wait for a few seconds and then I will just tell you which one will absorb the shortest wavelength. Okay, so that answer will again come from the spectrochemical series. So here first X donor has the lowest crystal field extravasation energy, then we have O donor, then we have N donor, then we have C donor. So this is the higher crystal field stabilization energy, means shorter absorption wavelength. More the gap between the, suppose this we have like two kind of thing, so this will be having the lambda 1, this is lambda 2, so means lambda 1 will be less than lambda 2, sorry, lambda 2 will be less than lambda 1, right? Because it will be the shorter the wavelength. And other way said that this is the strong, lambda 2 will be the stronger ligand, like a strong field ligand. So here we can see that this is F donor, this is O donor, this is N donor, this is O donor. So the correct answer is CONH3 6 plus 3. Now the number of microstate for 1G state is, How many number of microstate will be there in 1G state? I'll just wait for a few seconds. If you can answer, it's fine. Otherwise, right. So this is if what is the value of L? 0, 1, 2, 3, 4, 5. So for 0 it is for uh, for B it is 3, for D it is 5, for F it is 7, and for G it is 9. That is the number of microstate for 1G. Now from where it is coming, the number of microstate, right? That you can go ahead with. Cobalt L6 plus 3 is red in color, whereas cobalt L-6 plus is green in color. L and L correspond to. What is the reason for this? Wait for few seconds. So this one, like basically it has only 0, this has 3 plus 1, 0 minus 1, this is having 5 from minus 2 to plus 2 including 0, this is minus 3 to plus 3 including 0, this is minus 4 to plus 4 including 0. That is the answer. So this is one is the red in color, other is the green in color. Now we have to see that when once red will come means it is absorbing the green light. Once green is coming means it is absorbing the red light. Right? Now green has higher wavelength. Sorry, low wavelength. Low wavelength. And this having the higher wavelength. What does it means? Means this for delta L dash delta L. So delta L is greater than delta L dash, meaning that ligand L is stronger than L dash. Now we can see that definitely NH3 is the stronger than H2O. So that is the First option is correct. The first is that NH3 and second is that H2. That is the answer for this question number 30. Okay. In the isoelectronic series BO4 3 minus, chromium 4 2 minus, MnO4 minus, all member having intense charge transfer, the incorrect statement is CT transition are attributed to excitation of electron from ligand to metal. MnO4 exists charge transfer at lowest wavelength among the three. The wavelength transition is increasing as VO4 3 minus, CrO4 minus 2 and MnO4. The charge transfer of metal nucleus increasing in order like this. So what is the correct answer? So that definitely CT transition is attributed from the ligand to metal. This is the ligand to metal charge transfer because metal in the high oxidation state. Here it is plus 7, here it is plus 6, here it is plus 5. So metal are in the high oxidation state means ligand to metal charge transfer. Now this is the wavelength of transition increasing in order of this. So this has higher wavelength and here it is showing the shorter wavelength. Again the charge and the nucleus increasing in order of this, right? So how we will find that what is the like which? So if we are having the higher oxidation state means more polarization. So higher oxidation state means more polarization. More polarization. More polarization means less atomic orbital gap means higher wavelength. So lambda MnO4 will be greater than lambda CrO4 2 minus will be greater than lambda VO4 minus 3. So this is the incorrect statement regarding the question number 40. I hope you got it this. Okay. So now I will go to among the following according to the increasing DQ value. This is again like from the spectrochemical series. I will just spectrochemical series. Okay. I will just write again spectrochemical series. So we can see that what are the different kind of ligand. So this is the C donor, this is N donor, this is X donor. So C donor will come first. C donor will come first, then N donor, then C donor. The correct option is P. If the energy gap, okay, this is again like energy gas of octahedral complex is 3.48 into 10 to the power minus 2. What will the color of the complex? So you have the energy gap delta octahedral. Okay, from there you can calculate the lambda, and that lambda whatever it will come, this is the absorption lambda, and the complementary will be your color, and that is the violet color. The correct option is C. Just I think everyone should try and find out how to calculate this. Okay, so another way I will just give to the like hint. So E is equal to H nu or E is equal to Hc by lambda. Now you have E you have here, H is given, C you know that 3 into 10 to the power 8, lambda you can find out. So lambda is equal to Hc by E. From here you can find out lambda, and that lambda, the complementary color you have to find the color. So the ambidentate ligand SCN minus can coordinate to metal either as or A. This linkage isomer can be distinguished by UV visual spectra, IR spectra, fluorescence spectra, or not. The very simple is that if metal is bonded through S, if metal is bonded through N, they will be having different force constant and their vibrational frequency nu. So that comes under the IR spectrum. So this is the correct answer for this. Now, which of the following octahedral complex of nickel has the highest magnitude of delta O? Again, I think this is based on the spectrochemical series. Now we have to find out like what are the different kind of donor. Okay, then again we have to go to the spectrochemical series. Spectrochemical series. So here all the end donor is there. Now we have to find out uh, mm, which is the like strongest ligand. So the strongest ligand. So first thing is that this will not be there because it's a O donor, because these are N donor. Here it is O donor. So this is incorrect. Now NH3, En and BPY, in BPY, which one is having the highest magnitude of depth? So definitely if you look into the spectrochemical series, Ni bipyridine is the more stronger ligand compared to the NH3 and En. The transition observed in CO4 2 minus complex is A. Charge transfer, B is Laporte Farberton spin allowed, C is charge transfer, Laporte allowed, spin allowed, D is Laporte partly allowed and spin allowed. I think this we have already discussed. Okay, this we have already discussed. So again, here metal in the ordinary like oxidation state, so there is no kind of charge transfer is there between COCl for 2 minus. It is purely coming from the DD transition. Now second thing is that whether it is spin allowed. Yes, it is spin allowed and partly Laporte allowed, right? Because of PD mixing in tetrahedral. I have already told why there is more PD mixing in the tetrahedral compared to the octahedral. So the correct option is D. The solution of fullerene oxidizer are intensely colored due to. So fullerene oxide. So basically here there is no metal, so there is no d electron. No d electron. So here what kind of electronic levels is there? Sigma is there, sigma star is there, pi is there, pi star is there. So the first thing is that this will not be the answer. Okay, transition between D to D level. Charge transfer is also there, not there, because there is nothing, no metal present which is in the higher oxidation state and one is in the like one atom is working as the oxidizing, other is acting as the capping on small transition stem. That is also not correct. So basically the transition between the sigma star and pi star electronic transition is responsible for the intense color. I have already told that ligand transition has bandwidth of 100 centimeter, very low bandwidth, and they are highly intense because they are Laporte allowed, and spin allowed also. That's why their epsilon is very high, 10 to the power 5 to 10 to the power 6. That's why they are intense color. Okay. Which of the following is exceptional? Again, I will wait for a few seconds. and few answer that it is fine, otherwise I will just. So NCS minus is what kind of ligand is there? Okay, so this is normal ligand only. It can bind through NRS. There is no issue. H2O has only O. CO is very special and exceptional ligand. Reason is why? Because CO has low lying anti-bonding pi star orbital, which always form a metal carbonyl complex where metal is in low oxidation state, and here metal to ligand charge transfer occur. That is the exceptional behavior of CO in the following way. Number of possible microstate for P2. This I think I have already like calculated, or like P. So what is the N? N is the twice the number of orbital 3. So N is 6. What is R? That is number of electron, that is 2. This is the number of electron. So what is the possible number of microstate? Possible number of microstates, that is NCR, means 6C2, means 6 into 5 by 2, that is 15. So that 15 is the answer for this. Okay, if you have any doubt you can ask, that in between you can stop me and ask the question. If a transition of complex is occur in 493 nanometer region, then color of complex will be. Okay, so I will just draw the different kind of that I will draw the color wheel, and from there you can just easily know what is the color for it. So this is 400 to 430. This is violet. Then this is blue from 430 to 480. Then we have 480 to 560 called green region. Then 560 to 590 we have yellow region. 590 to 630 we have orange. 630 to 750 we have red. Now we will know that 493 is falling in the green region, right? So the complementary color red will be the color. The complementary color is nothing but your red. That is the answer. This is the way you can find out the answer. In metal carbonyl complexes, the electron transfer takes place from, that I have already told, that the metal carbonyl complexes MCOX is always having metal to ligand charge transfer. Metal to ligand charge transfer, where metal d electron transfer to the low lying anti-bonding pi star orbital of I CO. So Metal d orbital to ligand pi star orbital. That B is the correct answer for this. Okay. FeBpyCO3 is intensely purple color is due to. So now first we see that what is the oxidation state of Fe? Here oxidation state of Fe is 0. Means metal is in the low oxidation state. Always metal to ligand charge transfer will be there. That is very simple. So metal to ligand charge transfer is the answer. So that's it for today. I think if you have any doubt, you can ask me. I will explain. Otherwise, I will just sign out from the meeting. Do you have any doubt? Can you write in chat box if you have any doubt regarding the uh, any of the question which we have discussed? Okay, you can write in chat box how you whether you like the class, or is there any suggestion which I can adopt and it improves for you guys. Okay, yeah, I think thank you. Now I will be just signing out. Let first start the recording.